Let's get started. All right. So for the homework, it was to one, write these macros, and two, to restructure your project into good C structure. So first things first, I'm going to hang on, and I'll do the macros first. So the first thing was to write a define macro, and there was two define macros. Okay. Let me pull up to here and write some define macros. All right, question one was the max macro. I did that last night. To just hashtag define max. This time I'll do it within. Can I do it with an if statement this time? I probably can. No, 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 no. I can't. I have to do it with the ternary operator. If I want it to be at least good one line, I could do some
Do
messed
these
up stuff.
define statements have to be on one line?
So if you don't want them to be on one line, I talked about this briefly yesterday. You say you're writing a function or something, in you're defining into a function. So int a blah blah blah, and then a is your function name, and you have some other int, and then you want to have something on a new line. You use the backslash at the end of the line, and now you can continue on this new line right here, and it treats this as if it's all one line because this is one of the first stages of compilation is converting every backslash line that ends with the backslash into one single line in the source file. So if I run the preprocessor on this, if I have int a and then I break into these and I break that, and then I right here say, I don't know, return a. Now, if I actually call this and don't include stdio.h because it's gonna, do that whole big thing. And now if I say max AB, should just call this easy peasy. I'm really mad about how it does this. Like, do you see this when like I touch this, it like jumps this and this goes on to a new line? I hate it when that happens. It's some weird thing with the sizing where it's like just at like this one bad size, it does all of this jumping, but now it's fine. Okay, so yeah, we can see that effectively here, since when we put max AB here, it literally just copy, or again, you can put in anything here, func. Probably since it's a function definition, I would do it like outside, right? I do it somewhere over here. And now we're defining a func that takes an A and then just returns A, right? So it's something, it's just a return function. But we can have multi-line macros by abusing the hell out of this backslash, effectively. Okay, so back to actually implementing it. It was if A is greater than B, then return A, otherwise return B. And there you go. That's your max macro. Very straightforward. All right, so now for the for loop, which I don't think I was that clear about, write a define macro for variable size statement that generates typical loops over a single statement with only the variable name, size, expression, and statement to run. And then I gave an example of this on how this for statement, this would basically evaluate to this for loop right here, was my idea of this. So the way that I literally implement this is pretty straightforward. I'm going to take both of these. I'm going to hashtag define what I want. And then I am literally just going to go through this and put in exactly what I want. So this is the variable name. This is the size. And then this is S statement S. I'll just call it S. So my idea was int var, and then while var is less than 10, then do var plus plus. And this is a good place to
Should
actually
be
use
var
the
less
new
than
line.
size.
Oh yeah, because I had the 10 in there by default. Var less than size. And then your statement S in here. And huzzah. This is all I was looking for, effectively. It's so short that I can actually do that. So you could actually even put multiple statements in here because I put braces here in my definition. So effectively, if I put in, I don't know why I didn't do define, just did #4. There you go. So in here now, if I do 4 I to 10, printf %d I, and then semicolon in there, and we #include stdio. We don't have to do, but so be it. We can see that effectively this expands to this for loop that loops through 0 to 10 and prints out the numbers 0 to 10. So that was my idea for this for loop right here. For the actual correct program and reformatting everything, I didn't receive any submissions for that, but I assume most of you were able to get that no issue.
I sent you an
So,
entire zip file.
did you send that to me? I didn't see it. Hang on, let me look.
Why does it look like it gets
Oh, you
kinda,
did.
like, stringified at the end for the for
Because the issue is that this is an assembly display, and semicolon in x86 assembly means comment. So
Oh,
this they're interpreting this as a comment, but I'm just running the preprocessor on this. I'm not actually assembling. So it's unable to figure out that, hey, you're not this isn't assembly. This is like this syntax highlighting right here is assembly syntax highlighting. As in, these are all assembly keywords in some respect, and they just can't figure out how to interpret this. But that's why it looks like it's getting stringified here at the end, is because they think this is a comment, when in reality, this is just C code that we're printing out with the -e option on GCC, which
uh,
just expands preprocessor and returns the code after the preprocessor has been run. Yeah.
so for, like, define statements, when you put something in, parentheses, like, on a parentheses, you're pretty much just kinda, like, defining arguments for the macro?
Yeah, exactly. It's just like a function call, except it's text replacement, right? So it literally is just taking this first argument and subbing it in for whatever this first argument is in this thing right here, right? So
Mhm.
all A's get replaced with I's, all B's get replaced with 10, or sorry, this was, I was looking at max rather than 4. All vars, instances of all caps var get replaced with I, all size instances of size get replaced with 10, and all s's get replaced with printf%di. So yeah, this becomes very useful for enum definitions, where you might want to define an array of the actual enums that you can map enum numbers to, so you can actually print out what enums are. I'll do a demo of that when we learn about enums. I don't know if that is that tomorrow. I think that's tomorrow. Okay. Any
Alright,
other
cool.
questions about this before we move on? Okay. In that case, I'm going to move on to the topic for today, which is probably the most exciting topic that we've covered all week. Strings and things, and first things first, we're going to talk about the memory layout of C programs that once they are executing. So I'm going to take this beautiful image right here, and we're going to go over to MS Paint and talk about what is going on. So to help me along, actually, hang on. Okay, paint, good. Okay. I don't really have anything super fun planned out here, so I'm just gonna put this guy over here, and I'm gonna put Compiler Explorer over here, and move this guy down to the bottom. That way we have both of these at the same time. Okay, so for those of you who've never seen this before, I'm sorry. This is a core part of the C programming language. Effectively, once your program is written and converted into assembly, it has to get loaded into memory to actually run, right? And all of your variables need space to be stored in memory, blah, blah, blah. We covered this a few days ago, but we didn't go in depth into it. Today, we're actually going in depth to what happens when your program starts running, because we need to understand where strings are stored by the program, as well as this is going to be on the LinkedIn skill assessment. They do ask questions about the different memory segments of a running program. So I want to make sure that we can appropriately cover memory segments of a running program before we start anything too scary. So I think the first thing that's going to be very useful is to actually take a look at what this might actually look like with just int main and have there be an I. Dan, don't let that man's attendance count. Heat him. Return
What?
0. What?
Wait,
There was a person who was in here for like 30 seconds.
oh, my bot would have realized that.
Yeah, good, good. Okay. Anyway, all right. So effectively, when you have a function call, all of the memory used for variables gets initialized on the stack. So actually, if we get rid of dash e here and look at some of the assembly, which we don't actually need to learn how to read, you can just take my word for what this is doing. Effectively, what this is doing is this statement right here is allocating some memory on the stack for us. In fact, it's actually not, but if we call another function in here, it will be because it's optimizing that away. So I'm going to just recursively have main call main. And then this is a terrible idea, but this is the really important instruction right here. This basically says every time we call the main function, we allocate memory for all of our variables in this area right here called the stack. So you might see some lines here. This is the butt of the stack. This is where main actually starts off because there's nothing before main. So when you initialize your program in memory and you actually execute your program, the first thing that's going to happen is the memory for your program starts right here. Now, the first thing that happens, we can see main actually allocates space for its variables right here on the stack. So every time you're editing memory locations and doing anything with any of the variables in main has a what it's called a frame. So this is the stack frame of the main function. And as we can see here, they are allocating 16 bytes to main. So main is going to have a stack frame right here. And all subsequent function calls to main, and this is a recursive call to main, you can see I'm making down here, we are always going to allocate 16 bytes for whatever this I is every single time. So what this means is effectively we're going to actually get a stack overflow because main keeps allocating 16 bytes for itself until infinity, because obviously I'm not stopping here. This is infinite recursion. And eventually it's going to go crash into the heap down here and stack overflow. That's the end of your program. Your program will throw a stack overflow fault most likely. And this can have very bad unintended consequences. It's really hard to clean up a stack overflow. Your program basically will just crash. But I hope you can at least understand what a stack overflow is from this idea here, that effectively there is a region in memory where every time a function call is made and the functions know exactly how much memory it needs when it's called, it allocates that memory for itself on the stack. And if your function call gets too deep, especially if you're doing something like recursion, where you're allocating a ton of memory on the stack because you're having a function call itself, and each time the function calls itself, it has to allocate memory on the stack, immediately you're going to get a gazillion things allocated on the stack, and it's really likely that you're going to crash into the heap. So a stack overflow is almost always a recursive issue because you are most of the time going to have a crap load of memory here. Whereas on programs like, I mean, so Windows has a nice thing. So they do separate stuff with, this is kind of old segmented memory. The new thing is pages, so page heaps and everything. And we're not going to talk about that. But for the sake of our knowledge of the C programming language, we can imagine everything in this nice ideal environment where effectively the stack is up here, the heap is down here, and eventually, if you keep using the stack and the heap, things are going to crash into each other and cause a stack overflow. So that's the basic premise here of the stack. Does everyone gets the stack? We're all good on the stack. I mean, I think all of you already know C, so this I'm probably not saying anything new here. But what becomes fancy is, so I mean, we can also talk about the heap. So if I do malloc, calloc, realloc, all of that is editing memory on the heap. So when I allocate new memory on the heap, effectively when I call malloc, we're pushing this up. So new memory is being allocated from down here. And say I allocate an array of 20 integers, that's going to be placed right here. And then I allocate another array of 20 integers, that's going to be placed right here. And the job of the operating system is to actually then clean up the heap periodically when you call free. So when you call free, the operating system might see, oh, okay, you freed this area down here. Well, this would be a terrible idea, but they could say something like, oh, yeah, okay, so now that you freed this area down here, we're going to shift the entire heap down, or something like that. They wouldn't do that in practice. They have there's a ton of algorithms exclusively for heap management, but this is an example of something they could do. So effectively, they want to keep the heap down here as small as possible. So that's great. We have pointers basically so pointers to variables are pointers to any kind of variable on the stack. You can have pointers to memory locations on the stack, and when you have a pointer to something that's been mallocked, that's a pointer to something on the heap. Now, here's the fun part. We have other types of variables that we so far have not talked about at all. And these types of variables are so far variables that we've seen are variables that exist on the stack and variables that exist in some mallocked space, right, on the heap that we can access with a pointer dereference to a mallocked pointer. But there, all of the variables we've covered so far get deallocated at some point. So as you can see here, there is actually going to be a point at which, and they know that this is an infinite function, but let's say I write some int ret, which takes an int and just returns that int. So I'm going to take an I and I'm going to return that I. Okay, so this is actually a much better function to demo this with because this might actually work. All right, so this takes in the input, blah, 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 blah. Effectively, what I want to see is them transfer. Okay, so the leave actually in ret actually handles this for us. They're going to effectively, once the function ends, this memory gets deleted. So say I'm calling f or calling ret from main. Ret is allocating, they're not allocating anything because we're not actually calling anything in here. So effectively, the top level function that doesn't call any function, if it's at the bottom of it, it can edit this unallocated memory right here with literally zero consequences because it knows it's not calling anything and thus its variables will never be overridden. So that's what's going on right here. That's why you don't see any subtracting of the base pointer because it's just editing the memory on the very bottom of the stack without a care in the world because it knows that this can just be overridden on another function call. It doesn't have to clean up or anything because it'll just all be overridden. So this is an optimization. Ideally, though, they would subtract the stack pointer down to here so we could actually have an F in here, right? So we have the stack frame for F, which is kind of non-existent because it's been optimized out of existence, but we can just pretend there's a stack frame for F here. But effectively, once F returns, then all this memory returns to garbage, and hence we don't really care about it. And we can then call F again and then reallocate this with different values, blah, 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 blah. So essentially, the core takeaway here is all of the variables we've been looking at so far have lifetimes of basically the life of their function because when you call a so when your function ends, the variable effectively gets deallocated. This is why you can't do something where you have a function here. I have a variable in here. I'm going to declare int I equals 10. Okay. So I'm declaring that my int I equals 10, and you know what? I'm not going to actually take any parameters. I'm just going to say int I equals 10. And now what I'm going to do is I'm going to return a pointer to a local variable that's been declared in this function. So we should take a second to they should throw not an error, but this should be a warning at some point. Yeah, and you can see that this is a warning. Function returns address of a local variable. Now, why is this bad? Well, this is really bad because this variable ceases to exist effectively after this function is returned from. Because if we look at the memory model, what's actually going on here is that effectively I'm calling this function ret. I'm gonna actually erase a bunch of stuff. So give me a sec. So effectively, we have our main function. That's our first stack pointer. And then we have ret right here. And what's going on is ret has I allocated right here on the stack. But now, the second we return from, we also have the address. And that's effectively what we're passing back to main is the address of where I is right now. But then, once ret ends, this memory it doesn't get freed. It just becomes not owned by me anymore. So now when I make a new function call in main, say to another function, say I had another function, this function is now free to use the memory the space that I occupies. And this is an issue because we're returning I as if we're going to be writing to I, but I is a local variable. So the lifetime of this variable is until its function's call ends. So this is a core part of the C programming language is that the lifetime of a local variable is the scope of its function. So, as in, effectively, you should never have a memory reference to I out once this function ends, effectively. So that's why you can't do stuff like this. You can do stuff like this, but you shouldn't. It's going to be undefined because other functions are going to be using the memory spot that I is occupying right now on new function calls. So, what this effectively means is local variables only exist until their function ends. That's really the core takeaway that I'm trying to get right here. But there's something else we can do. There's other types of variables that exist for different lengths of time. And the type of variable that we're going to be talking about first is global variables. And I swear this all relates to strings in the end. It's not, the connection at first isn't super apparent, but I want to talk about global variables and static variables. So the first type of variable is a static variable. So effectively what a static variable is, and this is somewhat related to the static keyword in Java, is a variable who exists for the entire lifetime of the program. So if I declare static int I right here in my return function, now this actually isn't throwing a warning. So you're probably wondering, well, what the hell is going on now? You have a variable inside of this function. So the C language recognizes you're only able to use I within the scope of this function. But why isn't this being deallocated on the function return? Well, we can actually look at this and see in here that effectively, and I'm going to create a non-existent function that doesn't do anything. In fact, I don't know if this is actually going to work. This might work. They let me use void in here. Back in the day, you used to be. I think you can do that in C++. I don't know if you can do that in C, where you call a function that literally does nothing. So what if I write a function called void do nothing, and its entire existence is just literally it doing nothing? Is this going to allocate the stack pointer for me? Blah blah blah. No, they're too smart for me. Oh no, because it's afterwards. What if I call this first? Do it. Do it. Oh, okay. But what if I have int I in here? Will they do it then? Int j. There we go. Do it. Come on. Allocate for me. Allocate for me. There we go. Okay. So now we have some. I'm going to rename Brett to F just because none of these functions actually really mean anything. This is main. And this is going to be F. So effectively, F takes in. Oh, it doesn't take anything anymore. I don't know why that actually compiled. That was strange. Okay. So effectively, the core takeaway here is we have this is what? How do I redo? They're screwing me over here. I wanted to control Z over here, but I controlled Z over there. That break it? No. Okay. And let me pull this down a little bit. Okay. So effectively, here's what's going on here. So still doing this. Okay. I want to control Z on MS Paint. We have main. Our main function allocates a spot for its variable I, right? So its variable named I is stored right here. Now our f function allocates a spot for its variable that it calls J. But now we can see it also has this int I here that's not actually being used here. And the thing that's happening with this int I is effectively this int I isn't stored on the stack. It has a lifetime of its own independent of this function. So its memory location is independent of this function on the stack. It is actually being stored somewhere entirely differently. So if we actually take a look at this, we see there is a separate label altogether in the assembly called I.0, which has this reference to long 10. And effectively, what this is actually saying is that there is a separate variable in a separate memory location. And the location that this variable is actually in a segment called the initialized data section, which is also called the data segment of the program. So effectively, what's actually going on here is the compiler says, okay, you've declared this static. That means that this variable has the lifetime of the program. Even when this function ends, and it comes back, I will have the same value that it left with. So you often see static variables used for stuff like counters. So I can make a counter. So this is actually probably the number one application that you're going to see. So I'm going to have a function called int counter. And inside of this int counter, I'm going to have static I equals 10. And I'm going to, every time this function is called, I'm going to increment what I is. And you're going to see here that, what do they want? Blah, blah, blah. input type defaults to int in declaration of I. Oh yeah, static int I. I'm surprised that even works in the first place. So something that you would normally see with this is, so this counter function right here, I can basically call this counter function however many times I want, and however many times I call it is what ends up being the value of the function. So just to drive this point home, I'm going to make this big so we can actually see what's going on. Give me a second. Add new, execution only. And what we're going to be doing is returning the final value of counter. So effectively what's going on here is that you know what, I'll set this to 0 initially. But long story short, what's going on here is that every time counter is called, it increments this I by 1. But this I is only set to 0 the first time counter is ever called. Well, in reality, it's set at compile time to be 0. So effectively what's going on here is that this is a secret global variable, effectively. So it has a lifetime of the entire program. So I can basically say, all right, I'm going to call counter, and then every time I call counter, we're going to increment the counter by 1. And here we can see that actually this one returns 0, this returns 1, this returns 2, this returns 3. So what's really going on here is this function has a variable called I down here, which every time we call the function, it's adding 1 to this, and it ignores the assignment statement because the assignment only happens at compile time when it's initializing it on the data segment. So effectively, it's saying, oh, I equals 0, and now regardless of how many times you call this counter function right here in main, and reallocate the stack frame, what we're actually changing isn't anything in the stack. We're changing something down here in the data segment. So that's static variables. And it's the exact same case for global variables. So when I declare int I equals, or I won't do I because I've already used I for this counter. I use I in here for an example, for the static in example in here. What I really want to show is global variables though. So let's have a global variable called int num objects. So you could actually do this exact, actually I'll call it count, why not? So you could do this exact same thing with a global variable, but the detriment of using a global variable in this case is effectively that when you use a global variable in this case, you have to use a global variable. So a global variable is visible in the entire namespace and it leads to what we call namespace clutter. So you're never supposed to use global variables. Static variables are kind of like a hack. um, Matt said at 8:30 you would get screwed if you call the function again. What was that in reference to? I'm sorry, I wasn't looking at the chat.
I was thinking that if you call the function again, for example, you changed counter, but before you were defining
I
it as
can.
static and I equals 0, and my idea was, well, if you count counter again and it's not on the stack and it's in a different memory location, you'd essentially be defining the same, pretty much declaring and defining the same variable, but it's still in memory, so you're pretty much just redefining the variable, right?
The thing is, you're not redefining. This equals 0 doesn't actually happen every time counter is called. It only
Yeah,
happens at compile time.
so then
So
that was just my naive approach, or my naive thought of, the static
yeah,
keyword then.
so this is what really trips people up about static is that when you assign something to a static like this and it's a declaration assignment, this is assigned once, only once, and it's at compile time. So the compiler sees this and says, "All right, I equals 0 once," and then it will never run this statement again. It will treat I as a global and never set it equal to 0 unless you set it equal to 0 down here, for example. Then this literally resets it every time, and now you can see it's 0, right?
Yeah.
Yeah. So, but this equals 0 on the same line with the static int only runs once. So during compile time, it explicitly says, okay, we're going to have a 0 here in the data segment. And now every time counter is called, we're updating this variable in the data section, which is a special section just for statics and globals. So it's a bit more complicated than this, and we're going to get into this in a second. So int num objects equal. So I was going to do a counter with a global now, which is exactly going to be equivalent. So counter, and then I'm going to get rid of you, and then we're going to have the counter plus plus be right here. And effectively, what's going on? What are they yelling at me for? Blah blah blah. Oh, it's because this probably doesn't equal what 0. What do you want from me? Counter redeclared is different. Oh, I named it the same thing as the function. Okay, that explains a lot. All right, count. Okay, yeah, exactly. So same exact thing by declaring a global with an initial value to 0, right? Easy peasy. So this section is the initialized data section. So there's two different segments. There's the initialized data segment and the uninitialized data segment, which is called the BSS segment. And this is a holdover from some old compiler and process and like one of those 80s computers where they actually called this the BSS segment. All this means is the BSS segment is where they store uninitialized globals. So if you have, if for example, if I did int count and then didn't assign it anything right here. And I actually am surprised that it's running here. Most of the time, your BSS segment is going to be initialized to 0. So any uninitialized global is going to be set to 0. It's going to be all zeroed out. And we can actually see that that's happening right here. But effectively, this is no longer being stored in the initialized data segment because we haven't provided an initial value. It's being stored in the uninitialized data segment. So now our global here, because I'm not setting it equal to anything, is going to be stored here. So now count is right here. And it's same case if this was a static in I right here. So if I said static in I and then didn't set it equal to 0, but then did return I plus plus, we're in the same exact position where now we're no longer initialized data. We haven't set it equal to an initial value. Now it's an uninitialized data. So it's basically it's a location in the uninitialized data segment instead. So that's the instances where you're going to have memory that's in the uninitialized segment versus the initialized segment. Okay, so are we all clear on the 3 or 4 types of locations where you can store things? There's the stack. The stack is for local variables. Anytime you declare a variable inside a function during runtime, it's going to be stored on the stack. Anytime you malloc anything and dynamically allocate memory, it's going to be stored on the heap. Anytime you have a global or a static variable that you're not setting something equal to, it's going to be stored in the uninitialized data section. And anytime you are initializing it to some value, say you initialize your global to 3.1, blah, 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 I have this as like a float or something, it's going to be stored in the initialized data segment. Okay? So are we clear on all the different segments? I'm going to talk about text next. And there's one other segment, not segment, but something else I have to talk about. So we get on this? Fancy, fancy, I know. But all right. So if there's no other questions about this, I'm going to talk briefly about the other location that you can have things. So there is a keyword in C++ called extern. So the extern keyword, and I can't initialize things to an extern, effectively promises that there is a memory location named count somewhere in someone else's memory. So effectively, this is our program's memory, right? So our program owns this memory. It starts at some high address and low address, but keep in mind that there's a ton of other memory that other operating system processes own, both above and below. So, say your program wants to interface with some other program, or say it wants to interface with some DLL or something, right? The only way we can access memory that's outside of our allocated space is with this extern keyword. So effectively what this says is, hey, there's some other memory out there, and I promise it's gonna exist somewhere, but it's not in our thing. You have to go like hunt it down. And this is what happens during compile or during link time, effectively. They will basically link in all of the different addresses of things, and then this is where this really gets used a lot is with DLLs, which is dynamic libraries. So does anyone know what a dynamic library is? I'm sure you've seen a DLL file on your computer. On Linux, they're not DLLs. They're
It's what
called,
Windows uses for, like, everything. That's what
yeah.
Linux
So what a DLL is effectively is they load their own library. So in our case, you know how we compile our libraries in explicitly?
Mhm. Yeah.
So what they're doing is they load their library and all of their code in as a completely separate program, effectively. And then what happens is you want to make calls into their library and use their memory. So what happens is you're actually linking to somewhere else entirely in someone else's memory through the operating system. And that's what the extern keyword does. It says, okay, yes, effectively it's the same thing as a forward declaration, right? Do you remember our forward declarations from yesterday
Yeah.
where we
Isn't
were
that what,
declaring
I know I had
a
read
counter?
in a, article or a little thing that said pretty much functions are, like, by default externed when you forward or declare them, right? Or when you what was it? Pretty much like when you forward declare a function, or when you declare a function in general, it's, kind of like extern until you define it.
Right, and there is a bit more of there's some nuance to that. You can literally forward declare an extern function, extrn. So this would be a function that is in a DLL somewhere effectively. And I think I showed this off yesterday. When I go into my code and then I actually go to take a look at what's in stdio.h, you're going to see that every single definition and forward declaration in here is basically okay. So those aren't, but there is, where's my extern? I know that there's a lot of extern in here. Blah 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 blah. Are they not forward declaring extern in this version? Huh, I guess they're not actually doing implementation in here. This is all, yeah, so this is all forward declarations. Is this crimp defining to expect? Yeah, okay. They're using special compiler specific stuff, so this is a bad example. But effectively, back in the day when I was doing OS development, you had to use extern all the time because you were basically saying, my C program doesn't have access to this memory, blah, 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 but I promise you the symbol exists and it'll get linked in later. Now, so that's one of the uses of the extern keyword. The other use of the extern keyword is you do extern C, and then anything in this block is C code in C++. But in C, I don't think you can actually do that. There was once a time where you were supposed to be able to type in any programming language here, and then it would basically try and like use that as a separate program. But that program was discontinued. They
Is that just
never.
like an injection kind of
Yeah,
thing?
yeah. Effectively, it was like, hey, look, here's another programming language. Compile it, and it was great. Yeah, so effectively at link time, the compiler's like, all right, I need this symbol to exist, and it's not going to be in my memory well now. But okay, so extern, we're not actually going to really worry about extern. In fact, you'll almost never need to worry about extern at all. So just pretend extern doesn't exist. I just wanted to bring extern into the picture. So let's talk about the final segment, this text segment. So what's the text segment? The text segment is literally where all of your programming is stored, the machine code. So all of the machine code for your program lives inside of here. So all of the ones and zeros that define your program, that's here. So effectively, the program is in the memory, and then the program counter from the processor, for those of you who've done 404, is going through here, picking out instructions, sending them over to the CPU, and then executing them, right? And then operating on the memory up here, right? So effectively, this is how your program is this is how most operating systems are going to store your program in memory. Obviously there's some caveats now with paging, blah 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 blah, but this is the classic model of the C program running in memory. So now that we've talked about that, and hopefully you understand all of the segments and their pieces, blah blah blah, we're going to talk about strings, which are amazing. I love strings. So let's talk about strings. Let me get rid of all of this and we can begin our discussion of strings. And I think it's very useful for me to pull up. I'm going to pull up the compiler here so we can actually see what's going on here and I can talk about where strings are stored. So I'm sure all of you know this already, that strings are represented as const char pointer and then it's a name. So we're going to say str is the name of our string. And string literals are blocks of text between two double quotes. So, hello world, for example. We've already seen strings in our printf. Printf prints out strings, anything in between the semicolons, right? So you're going to notice up here that we have a string hello world right here stored in memory, and then we have a pointer to this string. So I'd like you to take a guess, though, where hello world is actually stored, what segment hello world is stored in memory. Any guesses on where this hello world actually is located?
It's a const, so maybe it's stored in well, actually, I mean, const wouldn't be. I don't know, I have a feeling that's not stored just from the stack. It's gonna be something different, like it was for the static. But
So
I
this
guess that's my
is
only idea.
this is actually this is a very good question. Effectively, this is actually stored. So there's multiple ideas here, right? So okay, number one, it's stored literally as contiguous memory on the stack, right? So when I call this, effectively what's going on is, okay, we remember how we were allocating space for I and j here? So now we allocate for our pointer, and then we also allocate for our string. So here on the stack, we're literally storing the characters for HELLO world, right, on the stack, and that's allocated there. That would be bad, effectively, because we have to set. So it's not like this, where if I have, let's have hello world, let me do a similar thing as const int I equals 0, right? This would be the integer example of this. And when we take a look at the machine code of this, and I'm going to convert, I hate Intel ASM syntax. Effectively, what we're reading in this is move the constant 0 into RBP. So it's almost the same thing as me asking you, where is this 0 stored? Do you know where this 0 is stored? Just the constant number 0? You can see it inside of these assembly instructions. And I guess I'll give away the answer. The answer is that these assembly instructions are stored in the text section. All of your program code is stored in the text section. So you can think of this as a move immediate, and the immediate value is stored with the instruction. But now things get spicy. What if we do the same thing with a constant string? Well, we see that there's this LC0 label up here, dot string hello world. And what this is actually saying is before the program in the text section, we are going to have the memory allocated for our hello world and our main function down here. So actually, hello world is stored in the text segment. It's stored up here at the very beginning of the text segment before any of the code. So you can see hello world stored up here before any of the code. And now here's something that's actually kind of cool. Because programs store all of their strings like this, any string that's actually in the source is stored. So if I declare another string here in a completely separate function, most of the time they're going to put that at the very beginning as well. So if I put function f and have this be hell b world down here, they put this down here. Most of the time they allocate them all right next to each other. I wonder if I try to get this optimized into existence. No. Okay, they don't even want me to optimize because they know they can optimize these strings completely out of existence. You can also have it reuse strings. So I think if I do this, are they going to reuse? Yeah. So you can see here that they realize that these two string literals are exactly the same. So they reuse one memory location for both of them. This $sign LC0 basically refers to the memory location in the text section. It's the pointer to the string, but this pointer is actually to the text section. It's not to any kind of it's not to the heap, not to the stack. It's a pointer that's pointing to something in here, which is pretty cool. So the thing about these null terminated strings, though, is strings in C are always ended by the null character. So despite the fact that I have hello world right here, these strings end with a \0 implicitly. So I don't even have to type that out because writing anything inside double quotes always will force it. So this dot string here basically forces this to end with a \0, as in when this string is actually stored in memory, what we're actually having stored in memory is HELLO space world blah 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 exclamation point at the end, and then this \0. But what this actually means in terms of memory is that each of these characters is converted to an ASCII character, and then the null character is converted to 0. So these are what are known as null terminated strings because they end with a 0 in memory. There's always a 0 at the end of their memory. So effectively, I wanted to show something kind of cool, and I'm going to see if I can actually get this to work. Here is my process explorer. So this shows everything that I have running on my computer right now. So these are all the EXEs that are running. Each of these EXEs on my computer basically has one of these guys, their own custom area where they have their own stack heap, blah 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 blah, somewhere in memory, right? So something that's cool that you can do is, all right, Discord, for example. Let's see if I can go to properties right here. Do they let me access the string table? So there's actually a section here called strings. And if I click on strings here, this is probably going to take forever to load because there's probably a ton of these. Okay, this is actually looks like it's crashing the application. I should do a less heavy. Can I do a less heavy application? Yeah. Okay, bye bye. Oh, that killed it. That's not what I was expecting. Let me pull it back up. Oh, I have it right here. System internals, process explorer. You know what I can do? I can literally compile one of my programs right here. I can make my own hello world like in 10 seconds. Let's do this. Okay, hello, goodbye. Okay, I'm just gonna do this really quick. So hello world.c. So we just want some string in this program, and I'm going to call it. You know what? Do I even want to write a program? Sure, why not? Int main const char pointer equals. I don't know if they're going to optimize this out of existence, though. Should I really try this? Hello world. And I don't know why I put the exclamation point outside, but chain 0. I don't know why I'm not putting my braces. Braces, please. And give this a name. See, okay, so now we have a program that has a string somewhere in memory. So when we compile this, we should still see that this actually, at least in Godbolt land, is going to compile to something that has the string hello world in it, in its text section, right? So now if I pull up my terminal, new terminal, and I compile this guy, and you know what I'm actually going to do? I'm going to commit the grave sin of, do I dare? I'm going to put this guy into an infinite while loop. That way he never ends, and I can actually investigate his string table while he's running. Okay, so I'm going to GCC this guy. GCC hello world.c. Give it to me. Come on. I'm rolling. This might actually break my computer. If this breaks my computer, I apologize. Okay, so this compiles into a.exe. Now I'm going to run a.exe. And huzzah, we're in an infinite while loop. But now I'm going to go over to Process Explorer and see if I can explore the string table of a.exe. So here is a.exe. As you can see, it's using 16% CPU power. I'm going to go into the properties, and I'm going to click on strings. And look at all of the fun stuff that we have in memory. And there's a bunch of GCC specific strings where some of these strings are behind the scenes stuff that the compiler puts in for you. All we want is the hello world, and my god, they put in a lot of different strings. I see the strings in memory. You wanna, this program cannot be run in DOS mode. That's a Microsoft specific. Oh, here it is. Okay, so here's the. Hi. All right. Moral of the story, don't screw with the string table.
Does your hello world work yet?
The second I clicked on hello world in the string table, my computer just yeeted itself. It literally, so it didn't brick, but what happened was I clicked on it, and then all of a sudden my cursor wouldn't move and my headset cut out. And I was like, all right, it's frozen, and it just wouldn't do anything. I had to literally go and restart.
Yikes.
So I've been having this issue with this computer in particular is terrible about this kind of stuff. Any other computer would be able to handle this fine. Oh, that's the wrong screen. Give me a sec. Screen share, screen 2, live. Okay. So we actually didn't lose that much, but effectively, all I wanted to show, all I wanted to demo was the whole hello world hullabaloo. So effectively, I'll just write that back in here. Strings in C, const char pointers. And these const char pointers are locations in what segment? What segment? Come
Oh,
on.
they're in the text segment.
Yes, exactly. The same way uninitialized numbers or number, when you set some variable equal to some number, it's an immediate. Const char pointers are located in the actual addresses, like the actual memory. The string itself is stored in the text segment, and then you have a pointer to something inside of the text. So if I do const chars hello equals hello world, we are able to use this to print f stuff. And the question that people often give is, well, how do we know the size of the string? How do you know that the string is a set size? Blah, blah, blah. There's a size of method. How do you know when to stop? The answer is because these are null terminated strings, every string is guaranteed to end with a \0. So you know that you're at the end of the string when you measure from the start of the pointer being the memory address that the string starts at on this H, and the null string being, or not the null string, the null character being the end of the string. So if you start on this and then start going through memory addresses, so that's for example why I can do stuff like hello. Let's actually, why not actually try this out? Printf, that's %c to print out characters, and let's print out hello sub 0. And what is hello world sub 0? And let me add a new, not compiler, I want a new execution only. Yeah, okay. So you can see we're printing out H here. So effectively, keep in mind how pointers work. The pointer points to the memory address at which the string starts, and then everything else, if we knew a size, we could store the size separately. But because we guaranteed have a known character at the end of this string, we don't need it. So if I do something like this, where I do printf hello, so I print hello 0, now I print hello 1, keep in mind that, again, these are pointers. So this is actually equivalent to dereferencing the memory location, which is actually a location in the text segment, where I can say hello +1, and this is equivalent to the subscript operator. We talked about this when we did pointers. So this is hello, the pointer to this byte right here, then the pointer to, so +1, so the pointer to E right here. And we can go till the end of the string. Let's do hello +12. And that might be one further than the actual thing. Okay, that's the exclamation point. And now if I try and print out the character at the 12th position at the end of the string, we see that it is nothing. That nothing being there is actually the null pointer. But let's not print these out as let's print these out now not as characters but as bytes. So let's print these out in 0. I don't actually know how you print out x. Is it %x to print out a hex number? So what if I do the thing before this, 11? This would be exclamation point. Yeah. Okay, so I think this is exclamation point in hex effectively. Probably be even better just to print it out in %d. These are the ASCII codes of our numbers. So this is the exclamation point, which I'm assuming is at 33. If we pull up an ASCII table, ASCII, we're going to see that inside of the ASCII table, we literally have, where is it? Blah, blah, blah. Give me my ASCII table. Where's my ASCII table? Man. Okay, here's what I always use. And exclamation point, as we can see, is indeed 33 in decimal. So effectively, we are just converting our characters here to our to numbers effectively. So all ASCII characters, these are all just represented numerically based on the ASCII conversion table. So when we talk about strings, I'm sure you guys know this already, we're actually just talking about a list of bytes in memory which have some byte representation in the form of ASCII. So the exclamation point is 33, and then the null terminator, the \0, is literally represented at position 12 implicitly as, oh, why are you mad at me? Blah, 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 expected, blah, blah, blah. Oh, I think I accidentally deleted a thing. Okay, yeah. So we can see that 0 actually is the null character in ASCII. They actually have a special character for it. It's literally called the null character. All right. So then, of course, we can overshoot this, but let's actually look at the structure of the program. I'm going to add a new compiler here. What do
Quick
you think?
question. Oh, sorry.
Yeah, yeah, go for it.
I was gonna say, can you print out, like, if you were to do like a byte representation, or like, could you possibly print out, like, since it's stored in text, like if you were to do pointer arithmetic over the string, could you like more like plus like 30 or something? Would it return like other elements of whatever's in that memory, like text
That's
or
exactly what I was about to show right now.
um
So take a look at this. Do you see what's stored exactly at? Oh, they bastards. I really want to. Okay, I'm actually going to do two strings. So let's do hello world, and we're going to do another string here. called meme, and we're going to put meme in right here. So we can see that we have two strings in memory here, hello and meme. And effectively, we're going to try reading from meme through the pointer to hello, because we can see here that they're going to be stored right next to each other in memory. So when I print out hello plus 12, I see that what's actually coming out here is the null character. But what do you think is that hello plus 13? Well, we're going to see that it's the M from meme. Because they are literally stored contiguously in memory. So now I can actually start reading stuff from the string meme through the pointer to hello, because hello, and meme are stored right next to each other in the text segment at the very start of it before the instructions. And now you could go beyond this and literally just start reading out literal machine code instructions once you get to the end of meme. So I can do 13. So this is index 13. This is 14, 15, 16. So just to show that this works, I'm going to type in 16 here. And you're going to see that we are printing out that final E. And 17 is, again, the null character because we're at the end of the string, so nothing prints out. But if we go convert this, if I convert that to D, it's going to stop. But if I go beyond this and I say 18, now what's 18 going to be? Well, they're not actually going to display it because it's probably going to be some number that doesn't have a nice ASCII representation. It might even be a null. So if I do, let's see, how far can I take this? If I do 19, how long until we get something that can be represented by a character? 13, oh, not 13. It has to be higher than that. What about 65, 64? So you're going
We
to
had
see
an
we
E.
actually start getting 65, H. Okay, yeah. So effectively now you're going to start seeing we get like these non-existent characters. And that's because we're trying to interpret machine code now as characters, which doesn't make much sense. The machine code would only make sense if we actually saw the machine code in machine code. So how can we actually we can actually play with this quite a bit. Remember when let's do something fun. I actually don't think object files are stored the way that I want object files to be stored, but we're gonna try playing around with this anyway. I don't have a hex editor on here. Crap. All right, I'm gonna just install the hex editor extension on VS Code so I can actually show you how this works in memory, because this is pretty cool stuff. I do like screwing around with all of the memory. I'm just hoping I don't brick my computer again. Okay, so I'm gonna use the same program we had, but we're not gonna run this program this time. Actually, you know what? Let's use the program that we just wrote. I don't even know why I have this struct here. Ignore the struct. Struct, goodbye. Struct away. All right, blah 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 blah. Come on, come on. All right. So now what we are going to do is we are going to compile this to an object file now. So I'm going to gcc-o hello.o, and the name of this is hello world.c. All right. So we're going to compile this to an object file. Give it a second, and there's our object file. Now, what we're going to do is we're going to open this with a text editor, but I don't have a text editor, or a binary, not a binary, a hex editor. So I'm going to go install the hex editor, and I know this extension exists because I have it on my other computer. Microsoft gives you a hex editor? Oh yeah, this is the default one. Okay, this is actually the one I have. I was like, oh, so fancy, but no, this is the right. Okay, I remember working with this. So now I'm going to hit open with hex editor. And now we are going to see we are actually inside of the binary encode. So this is the object file. So somewhere in here, there is going to be literal machine code. And what I'm going to search up is the string that we have written in here. So I'm going to search up. I want to, God, can we, let's be adults here. I know it's in here. I know hello is in here. You can't lie to me. There's a whole symbol table here, blah, 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 blah. I'm just looking for the code effectively. All right, so this is all the issue. The issue here is look at all of these additional strings that the compiler puts in for us. So the compiler is doing some big thing, and it's being like, oh yeah, we were compiled with MinGW, blah blah blah, on this operating system. And obviously, this is all for Windows, and just when things link, it needs to have all of this information. Blah blah blah. It's gonna be like in the middle here somewhere. Subsystem checks, don't care. Blah blah blah. All right, this looks like machine code. This could potentially be machine code. Let's see. there's a gazillion things in here. This was a terrible idea. What if am I sure I can't control F? I really wanted to show off where it was in here. What's this tiny magnifying glass? Oh, search in hex. No, search in text. Man, I knew it was in here. All right, here it is. So effectively, here's our string right here. Wait, wasn't it hello, hello? What? Did I forget to recompile? Terminal, new terminal. Not new terminal, I want to use the one we already had. GCC, hello, hello. You shouldn't be in here still. In text. Oh, there's another one. I know you're in here. Why are there so many hello world? Oh, it's saying it's the name of the file that was compiled. Okay, I'm like, what? Why is this in here? In text. All right, so we're just gonna go through all of these until I find it. Oh, would you look at that? I think that's main right there. File, hello world, main, text, BSS. Okay, these are all the segments right here. Are these pointers to the start of the segment? Come on. Why isn't control out? Oh, I wasn't pressing control. That would explain a lot. All right. So next. There is no next. That's concerning. Where is it encoding this string? Is it like magic encoding this string? I know for a fact that it can't be magically encoding this string. File hello world. Here's the main function. So this is literally the code that we have in here for main. I'm not telling it to compile with any symbol, but I guess it's the symbol table. Okay, you know what? Instead of sitting here and wasting more time and looking for all the fancy stuff, all you have to know is that this is machine code. We don't really care about the machine code. Here's some other files and blah, blah, blah. But I thought it would have been cool to show off where it is in the text segment, but obviously there's more to it that I'm not fully aware of that GCC is doing behind the scenes. I thought it was going to be nice and easy, but we can see that it's easy. We can easily verify by just printing out things beyond where they are in once they're loaded into memory. So effectively, we're able to get M from the pointer to hello. That was the big thing that I wanted to show. So with that, does anyone have any questions about? So I didn't mention this, but const char effectively means that you are not allowed to edit this. And the reason you're not allowed to edit this is because it is in the text section. And editing the text section is extraordinarily off limits. Can you imagine? Do you know why the text section is incredibly off limits? Is there any guesses as to why you wouldn't want people writing to memory locations in the text section? This is
Like,
actually
isn't that where the rest of your program is?
exactly.
It's
So
overriding your program.
imagine the field day a hacker would have if he could change your code in the section that this code is being stored in. So effectively, the operating system tries to lock things down as much as possible and says you cannot write to the text section. In no circumstances is your program allowed to edit itself, basically. So you can't change your own memory locations, blah, blah, blah. So what this effectively means is you're completely locked from being able to do anything super, super fancy here. So you cannot say, oh yes, I'm going to change, because remember, this is an instruction right here, and if we did a pointer dereference, then I could start actually editing the machine code from the C itself. I could say hello plus like 65 equals 12, and this is going to be illegal because it's assignment of read-only location, which, yeah, because this is a const pointer, which means I'm not allowed to edit whatever this is pointing to. So the way, again, that you read C types is actually backwards, with the exception of const. Const can be before the type, but what this actually means is char const pointer. And what this actually, you read C types backwards. This is a pointer to a constant character, as in this h can't be changed. But what this really means is it's a constant character array because there's more constant characters in line after it up until that 0, right? So that's const chars. That's basic strings for you. It's not that hard to get a handle on, but it's always just important to remember this kind of stuff. So obviously, you can allocate your own strings. So say you don't want your string to be stored in the text section. say you want to dynamically allocate a string and have a user input a string. So you might remember scanf, and we were playing around with scanf at the beginning, and we were just scanning numbers in, right? But let's get more fancy. Let's say we want a user to input a string. How do we have a user input a string? Well, the way we do that is we have char, and then normally we do a fixed size char array. So we have a char array of size 100, call it user input. All right, that's user input. And then when we do scanf, we effectively say, all right, I'm going to scan %s is string. So it's interpreting whatever thing we put in here as a string. So I'm going to scan to this address right here. And effectively what this says is store the string in here. But what's really going on here is we've allocated on the stack, because this is a local variable, right, on the stack, 100 characters for the user's input. So now what effectively is happening is when this function gets called, it's saying, all right, I'm going to allocate all of this space, and then I'm going to read something to this spot on the stack. And then now in the function, I'm going to actually use that, right? So now it's going to do some manipulation with that string right there. So again, remember when we declare arrays, this is actually of type char pointer. The user input itself is a pointer, and we can use it as if it's a pointer. So I can dereference this to get the first character of user input, right? So this would effectively be me reading whatever the first character of user input is. So if I actually printf this, and I printf user input as a character, %c, what this is actually saying is, all right, take in something and then print out the first character of it, and we can actually do this. I'm going to actually put that in right here. So if I put in hello, we should see that std out is going to be h, and it's not question mark. Hello? Hello? This is somewhat strange. Is it because I don't have the enter afterwards? Is this actually on the input, or is this on, what am I looking at here? Why do I feel like that's not, that wasn't the input? Okay, that's why. I'm like, what's going on here? Okay, yeah, there we go. So as we can see here, H, we're putting in H here, okay? So effectively, all this is doing is we've allocated this on the stack. User input is on the stack, 100 characters for the stack. Now, you might be wondering what happens if you go over this limit. Well, scanf, I actually don't know if scanf throws an error if you go over. I don't think it does. As in, you're screwed if your user inputs something really, really long here. And I think there's actually ways to buffer against this with scanf, a version of scanf that takes a maximum length and then is going to fail if the user puts in something over the input size. Because obviously, we don't want it to scan into memory indefinitely, because what is in memory after this in the stack, this is a pointer to something that's on the stack. If we go over, yes, we can go into that unallocated memory, but we're probably potentially can crash into the heap, and that's going to be an undetected stack overflow. You're rewriting areas of your program, and blah, you're done for. So ideally, you want to make sure that when you do a scanf, that the user input for a string is always going to be shorter than the amount of memory that you've allocated. And there are, I believe there's ways to do this. If we look up scan, I don't know why I can't spell.
They're
Scan,
all in the like the string.h library. There's like they have like an n in them or something. Because I know stringcat has like string ncat or whatever, and then like all the things
yeah,
have like
yeah.
the buffer size. It's
Scanf with buffer size. That's effectively what I want. I'm pretty sure butter size, buffer size. There we go. How to prevent causing a buffer overflow. SN_printf. Pike discuss this problem. Correct buffer size by passing the scanf functions in effect. All right, so here they're allocating a constant character, or not even constant, because we're writing to this memory location, obviously. Format 32, buffer length equals 0, and then they're using SN_printf with a format, blah, blah, blah. We don't really care about this. So they have a scanner that is, what does SN_printf actually do? What is SSScanf? I feel like that's what I'm looking for. And I'm going to look at the C++ reference one. Is this... Oh, this reads data from a string. Okay, so this is like sprintf, effectively, is what I'm looking at. But all right, so effectively, long story short, this is kind of just an edge case. So we're not going to spend 10 minutes on this. I thought it was just an interesting thing to point out that scanf can go over and you can cause a lot of memory issues. This is like the number one C issue is when you go over the amount of memory you've allocated. So, for example, let's say that I allocate 5 characters right here, and now I'm also going to allocate a char C here and leave this guy completely empty. Okay, so I'm actually going to have this guy be volatile because I don't want him optimized away. So volatile char C. And now I'm going to scan 5 characters of user input. And you know what? Yeah, sure, why not? And effectively, what we're going to see happen is if I try scanning more than that, and I'm actually going to output C right here. So I'm actually going to scan 6 characters of user input. So here I have hello, 1, 2. And we should actually see that it might. Are they actually going to prevent an overflow? Let's see. They might actually prevent an overflow. So I'm scanning in 5 characters. 1, 2, 3, 4, 5, 6, 7. No, this should be causing an overflow. I don't know why it's not. They're probably doing some kind of. Let's see. I actually have to look in memory and see what they're doing here because this would. Ideally, these should be right next to each other. The volatile might actually be ruining it. Let's try removing the volatile. Okay, yeah, so here we go. So effectively, what's actually happening in this program, we can see that C is getting the number 1 written to it. And in fact, if I put the letter C right here, we'll see it gets C written to it. And what's actually going on here is in memory on the stack in, let's go to, let's actually take a look at this in Paint because this is a good example of how C programs actually work. I'm going to do one of my memory diagrams that I did on the day where I explained what pointers are. So effectively what's happening is when this function is called, we allocate spot on the stack for those 5 characters. So first things first, 5 memory locations for these characters, right? So 1, 2, 3, 4, 5. Sure. Okay, so that's 5 memory locations, and that's user input, right? So this is user input. But so user input being the pointer to the first memory location right here. The other thing that we allocate on the stack is a single pointer for a character C, which is actually when we allocate it on the stack is literally right at the end of this. So it's at whatever, let's call this M for memory location. This is literally at M plus 5. So effectively what's going on here is when we run scanf into this, if it scanf's over, it's actually going to start reading into all of this memory on the stack right here. So when I scanf hello 1 2, it literally goes HELLO 1 2 into whatever this is, which we don't even know what this is. This is some other thing off in no man's land. And effectively then when I print F and say, hey, what's in C? It says, oh, 1 is in C because we've scanned F over into a completely separate variable. So basically this is a scanf overflow where you're scanfing into a separate variable by accident because it doesn't check the size of the input effectively. It doesn't have any way of knowing that user input is only 5 long. And this is kind of what's so dangerous about C is this is a completely unintended consequence. You could do this completely by accident and then have your user completely brick your program because they put in a string that's too long for you to handle. And then by doing that, they've edited the numbers in memory locations that you did not think that they were ever going to be able to access. So you're basically editing variables without actually editing variables. When you look at this line right here, you just think, okay, yes, this is editing this array right here. But no, this can also edit all of the memory locations after it if you're not careful. So that's that's some dangers with the C programming language and strings and scanf. But all right, next things. What do I want to discuss next? We can talk about some fun stuff. I guess we should talk about. Okay, it's 9:25. So I think I've given a decent overview of how strings work. It's literally just character arrays in the case of you reading in user input. I mean, same thing if you want to malloc your own strings, right? So say you have some user input and you don't really know what you. So I mean, let's say for example, when's a good time to malloc a string? say you literally have no idea how big the user's input is going to be, but you want to ask them beforehand. So you basically say, all right, I'm going to scan FD and I'm going to read in int size and give the size here. And I basically ask the user beforehand. I say, hey user, how big is your text that you want to enter? How much text? So this is like the character count. I'm asking the user how much text they are planning on entering. So if they're planning on entering a lot, they put in a big number here. Obviously, you'd never do this in a real program. What you would actually do is try and use the operating system to read how big the buffer is before you copy it into whatever your buffer is. But we can do something like this where we have a size, we want to know how much text is going to be put in. And then effectively what we do is once they give us the size, then we allocate a character pointer using malloc. So we actually allocate a space to put this. And we're kind of trusting the user to follow this and only put in as much as they can. Otherwise, you're writing into the heap, and that's even a bigger. It's better to write into the empty stack. Writing over in the heap, if you go over in the heap, you're writing into other dynamically allocated memory for your program. And that's an even bigger what the hell is going on moment because you don't manage that memory. The operating system manages that memory. So while I can see very easily, oh, okay, user input is right next to char C, I'm probably allocating into char C by accident, and this is overflowing. The memory in the heap, you have no idea what order things are on in the heap because the operating system is completely managing that. So if you overflow in the heap, that is not good. Don't write and overflow in the heap. And to be safe, you might even want it to be const char so you can. Well, no, you can't do that because you actually have to write to it, and you can't just initialize heap memory. that is not a thing. Okay, so you can have a char pointer, and we'll call it my string. Or maybe user text would be something better, more descriptive name. User text, right? And that's going to be whatever the size is. And we are just going to malloc a char pointer of size user text. Malloc user text. What am I doing wrong here? What am I doing? No, size of char times size. There we go. Okay, and I need to have that work. I need to hashtag include stdlib.h. Okay, so now effectively I'm asking the user how big they want their thing to be, and I'm going to say 12, and now it's going to dynamically allocate a spot for a character, an array of 12 bytes on the stack, not on the stack, on the heap, and now we can actually scan into the heap. So now we actually scan f user input %s, and we're going to scan into user text, which is already a pointer, so you don't actually have to get the memory address. Remember this. This can be a big screw up if you pass the address of the pointer, because now this is a pointer to a pointer, and this is not... Excuse me. This is not a... You're then writing to this memory location on the stack, not the memory location that's being pointed to by that memory location, which is on the heap. So we're going to scanf user text, and so now I'm saying, hey, I want to allocate a string of size 12, and so that string could be hello world, blah blah blah. This should be size 12, because scanf is going to automatically append that null character onto the end once it scans it, right? So this is an example of how you could dynamically ask a user how much text they want to type rather than just being like content and saying, okay, I'm going to have 100 spots reserved. You almost always see, though, in real C programs, they almost always just pre-allocate like 500 bytes. They're like, okay, I'm going to have 500 bytes of characters, and I'm going to read to this and just pray that they don't violate me. And it works most of the time, but it's terrible practice because this could easily overflow. Anyway, that is strings, effectively. I think I've covered strings pretty well. The only other thing we have to cover is, let's see, the string library. So in C, we have strings, but we need a way to manipulate strings. And that is all done through the library known as string.h. So string.h doesn't give you, unlike other programming languages where strings are actual constructs of the language, in C, they are not actual language constructs. They are literally just const char pointers, or char pointers for that matter. So you can use your own char pointers. They don't have to be const chars in string.h. And effectively, you guarantee, though, every time you use a string.h function, that whatever array this is pointing to of characters is always going to be null terminated. If it is non-null terminated, you are screwing up, and that's going to crash your program, and it's going to crash inside of the library function because of what you've passed into it. So let's briefly look at the actual C library for null terminated strings, which is the strings library. So effectively, we're not going to be talking about multi-byte strings, nor are we going to be talking about wide strings. Effectively, these are for like Unicode characters and stuff. We're just going to be talking about nice old ASCII strings that contain ASCII characters. So let's briefly talk about the functions that are stored in this library. I'm going to post a link to this if you guys want to look it over later, and it's going to be very relevant to your homework. So the first thing that we have here is character classification functions. These are really basic. So this is like effectively. Oh, and they have. Why is this defined in C type? I assume it's also defined. I hope it's defined in string.h, because it would be kind of silly for them not to define this in string.h. Is only string manipulation in string.h? So this is all in string.h. Oh, okay. So we're going to just ignore this then, because we don't actually need string character classification. All we care about is the stuff that's in string.h. So that's going to be string manipulation, string examination, and character array manipulation, which is exactly what we are going after here. So the first thing that we're going to look at, and I probably should talk very briefly about the conversion functions. So effectively, we need functions, as in every programming language, to convert an int to a string to an int, and vice versa, right? So these are all defined in stdlib. These are some of the most common functions. A2f is effectively, it converts a string to a double. So say your user inputs 3.141, and for some reason scanf can handle this internally, but if instead you want to actually read this into a float for some reason, or a char, so you have your char c equals, let's just have a buffer of 50 bytes here, and we're going to scanf our c, and we're going to read a string in right here, so %s, and we're going to be passing, again, that's a memory location. C is already a memory location. We don't need the address of C. What are they whining about? Implicit declaration. Oh yeah, of course, because I got rid of hashtag include stdio.h. Okay. So let's say I want to actually read. So now I have the characters 3.142 inside of this character array right here, as in it's a string. It's a null terminated. Scanf automatically null terminates it. Obviously, the better way to do this would be to just read this directly into a float with %f from scanf, but we don't care. We're just going to, for the sake of this example, do it this way. I'm also going to hashtag include std lib.h right here. And what we're going to do now is actually run this conversion. So the function a2f, effectively, what all this does is it takes in our null terminated character pointer, which is C, and is going to convert it to a float f. So now I can say f equals a2fc, and I can probably print this out as well. So I can print this out as a float now rather than as a string. So I'm going to %f here, and we're going to print out f, and this should be print, not scan. Print f, %f, and as you can see, it prints it out as a float. So despite the fact that we store it as a string in here, we do the conversion from a string to a float, and we print it out. So these functions are basically all the same. Effectively, all they do is, so a2f is string to float. Anything that's prefixed with a means string for some reason. This is a weird holdover from some convention in the 70s, as most stuff in C is. So you have a2i, which is string to integer, a2l, string to long, A2LL, string to long long, um, STR to L, I don't know why, converts a byte string to an integer. What? What's the point of this? Until str string long char pointer end. Oh, so this is like if it's not null terminated, I guess. I don't know. Is this because this you're required to put in the pointer to the ending value, which means that I'm assuming this is like non-null terminated. So A is null terminated, str is non-null terminated. Anyway, we're not really that concerned. This is how you can convert strings to integer types. I believe there's a reverse of this somewhere, but I appear to have lost it. You can, oh, well, yeah, there is. It's called sprintf, and it's defined in, I think it might be defined in stdlib. Anyway, there's this great function. So basically, long story short, if you want to convert anything, so you know how printf prints things to the console as strings? Well, say you want those as your own character array instead. All you have to do is sprintf, and then the first parameter to this is going to be a character array. And effectively, what this does is it reads whatever would have been sent to the console into this string right here. So this converts a float into a string, and you can do this with any kind of character here. This could be an I, blah, blah, blah. So that's, I would use that as the reverse. I think there might be a specialized function to do the reverse, but I always use sprintf instead because it's way more convenient. Anyway, enough about that. Let's take a look really briefly at some of the other functions in this library because we have quite a bit to go through. So it's actually, I'm almost terrified that there's not going to be that much to talk about here because these functions are pretty set. So the first function that we're going to talk about is string copy or str copy. And we're not going to worry about str copy underscore s. We are only going to be talking about str copy. So effectively, what this does is it takes a pointer to a destination, so a char pointer to a destination and a char pointer to a source, and copies the string from one location to another location. So think about for a second how this actually looks in memory. So we have our character pointer C here, right, in memory. And we can, let's make this even spicier by having this be a pointer. And again, you're forced to make this a const pointer because whatever constant you put here is always going to be stored in the text section. So I'm just going to say hello world, right? So I'm effectively here, what I'm saying is we're storing hello world in the text section. I think I could do something fancy and say something along the lines of I kind of don't want to do this, but I'm going to try this for the sake of argument here. What if I make this a char array? I think this gets stored in, yeah, okay, so now take a look at what's happening. It's literally storing each individual byte of hello world in I don't want this in Intel syntax. That's what I'm whining about here. Effective, what did I uncheck? I don't want it. I don't want to compile to binary. Please. Okay. So what are we doing here? Okay, so effectively this is some kind of string representation of hello world. And all that's happening here is it's moving hello world byte by byte onto the stack every single time. So instead of encoding hello world here, it's encoded like in the instructions, which this is actually not what I expected to happen. This is terrible. Don't do this. All right, we're going to go back to our const char pointer instead because this is much nicer. Anyway, long story short, effectively what we're going to be doing here is we are going to be doing a string copy. So this is at some location in the text section, right? So let's say we want to make a copy of this, right? Because so there's two ways we could do this. I mean, the first thing is because this is literally a pointer, we could just pass a pointer to the thing, a const pointer, right? So if we have a function and we want the function to actually be able to read this, you could do something along the lines of saying void my func, which is going to take some const char pointer my string. I don't know why I can't type today. My string, and we're going to just print that because why not? Printf %s and my string. Okay, So effectively, all this is doing, and we're going to call my func with C down here. Pretty straightforward program. So effectively, we're just calling a function that prints out this string. But there's actually no copying going on at all. We don't ever have to copy my string. My string is still stored in the one location it's always been at, which is in the text section right here in LC1. Effectively, what's actually going on here is no copies being made. What's really going on here is we are, again, passing the memory location to this, right? That's exactly what pointers do. So you're not actually copying the string per se. It would be more of a copy if we did something where we actually were receiving like a bunch of bytes for the string, right? So now this is a function, and this is actually the wrong syntax. We have to put it after the variable name, and I despise that. And this is actually ruining the thing because, long story short, we can't pass the pointer anymore. This is effectively saying, okay, I have some set of 50 characters. I'm going to copy every single of those 50 characters. We're not actually passing a pointer anymore. We are passing 50 individual characters as an array right here. So this is actually making a copy of whatever is in the array that you're passing, is my understanding of it. There's could be some weird stuff with copulation here, but no copy is being made. So if we actually want to make a copy of our string rather than just passing around pointers to it, so say we want this string to be mutable, say we want to actually edit hello world, right? So this is one of the number one things we might want to do. I want to start playing around and editing hello world. Well, let's actually take a look at this really quick. I'm going to try, so I'm a printf hello world right here. So I'm going to print out C right here. Let's say I want to change that H right there to, and they're yelling at me now, but I'm deleting that function, so too bad. This prints out hello world. Let's say I want to have this print out jello world instead. So I want to change the first character of hello world, C sub 0, to a J. And guess what? They do not let me do it. And that's because I didn't have it as an actual character, but effectively, because this is a const char pointer, I'm not allowed to edit this memory at all, even though it's in memory. So effectively, we're unable to actually mutate this. So now we actually want to start mutating this string. We're going to have to actually move this string somewhere else into a mutable location where we can copy it. And where better to move to a mutable location and copy this string than using str copy, which copies one string into a second string. So to do this, I'm going to create a mutable location on the stack. So it's going to be a char pointer to, let's say, so we actually know the length of this beforehand. So I can actually use another string function here called strlen. And this is the most basic examination function. It returns the size of a string. So effectively, I can actually do this dynamically. I'll use the heap instead to demonstrate how you can do this. So what I'm going to do here is, first things first, I'm going to get the size of this string. But I'm going to do it as I allocate a new location that I can edit on the heap. So I'm going to say char pointer my string equals, and I'm going to have it be malloc. So I'm going to cast a char pointer malloc, and then I'm going to do size of char times, and this is the big thing, I'm going to multiply it by the size of the string. So effectively what I'm going to do is do strlen of C. And effectively now I'm dynamically allocating a new string on the heap of the size of this initial string. And now what I can do is, because I know these are the same size, because I literally allocated them to be the same size, is I can copy the content. So keep in mind, when I malloc, this doesn't actually initialize the string. I actually need to fill in and copy that content over into my new string, right? Because this is in a completely different memory location. This is in the text segment. This is in the heap. So I'm going to copy over the contents of C into my string using the strcpy function. So strcpy, I think it's strcpy. I'm not going insane, right? It is strcpy. Okay, very good. So effectively, what we're doing now is moving a constant string, character string, into something I can mutate in the heap. So the first parameter is the pointer to the destination. And so this is where we want to actually move this string. So I want to move C into my string. So my string is the memory destination of this string. And the thing that I want to move is C. So we can imagine very easily what's actually going on inside of string copy. All string copy is doing is it's a big for loop that says, okay, I'm gonna move byte by byte every single thing here. Oftentimes the operating system has this optimized, so they're moving big chunks of memory at a time using specific machine instructions behind the scenes. But for a simple implementation, you could literally think of this as a big for loop that says, okay, I'm going to move everything, or you could think of it as a while loop. I'm going to move character by character. I'm going to look at H, move H to the first memory location of my string. I'm going to move E, I'm going to move this until I hit a null character. And the second I hit a null character, I stop doing my copying. Or in this case, we know for a fact that my string has the exact amount of size we need because we've literally allocated string length to be the same size as our character pointer here. Okay, so now I can actually do that edit that I had been wanting to do for so long, where now I can actually change my string because this isn't constant, this is in my controlled area, we're not in the text section. I can now say that my string sub0 is equivalent to j, so we can set this. And now I'm going to be printing out my string, and we're going to see now that it is Jello World. Beautiful. Okay, so this is a very brief example using strlen and strcopy. So again, string copy copies the load contents of the second string into the first string, effectively. And again, these are all pointers that we're working with. So it's the thing pointed to by C is being copied into the thing pointed to by my string here, right? Okay, so what next? Let's do okay, so I did string copy. The next thing is probably string cat. So string cat is actually pretty straightforward comparatively. Let's see. It appends a copy of the null terminated byte string to the source to the end of the null terminated byte string pointed to by desc. Okay, so and then it returns right. So effectively, you have to have enough room here though to actually do this, which is this is the big thing. So I'm going to have to now allocate. So say I want to, so this is just string concatenation, right? In other languages, you use the plus operator for this. Let's say I want to join hello world. These are separate strings that are being stored separately. Okay, so hello and world are both being stored separately. Put a space here, why not? Effectively, I'll have this B, so I'll have this BC1 and I'll have this BC2. So I want to concat these strings together. I want them to be one big happy string all together. But effectively, there's going to be issues here, and the issue is going to be the fact that, let's see, so it's a copy of the source onto dest. So SC0 replaces the null terminator at the end of dest, right? Okay, exactly. So effectively, we need to allocate enough space for this string. So again, there's two approaches to this. You literally just declare the char array here, C, and make it as big as you want and pray for the best, or you dynamically allocate based on the amount of space that you know you need. So I'm going to dynamically allocate here and say that this is C3, this is going to be our combined string. So how much do I need to allocate? Well, I need to allocate for the number of characters of string 1 plus the number of characters in string 2 because I'm combining them effectively, right? So I'm concatenating them, and I can actually subtract 1 from this legally because, and they're getting mad at me because of, what are you so mad about? str copy. Oh, because my string isn't a thing anymore. Anyway, long story short, I can actually subtract 1 from this because we're getting rid of one of the null terminators. You have to keep those null terminators in mind, but that's not really important. If we allocate an extra 2 bytes, it doesn't really matter. So I'm going to allocate for the size of the first string plus the size of the second string, and now I'm going to str cat, C-A-T, into C3 from, I guess I could do a copy first, why not? So yeah, effectively what I'm actually going to do here is I'm going to copy strcpy cpy hello into this new allocated string first. So I'm going to copy C1 into C3, and then I'm going to append the contents of C2 onto C3. And now if we print out the entirety of C3, and I'm getting rid of this thing right here and adding in a semicolon because you need semicolons, we see that we've successfully concatenated hello and world into one string right here that is stored in dynamic memory. Also, I'm being a terrible person right here because I haven't freed any of the dynamic memory I've allocated here.
I have a
Okay.
question quick. You
Yeah.
might have said it, but why do we need to dynamically allocate memory to C3?
Okay, so this is a terrible example for this because we know the size of these at compile time. So effectively what I can say is, okay, I know the size of hello and I know the size of world. I am literally going to just say char C3 and have this be the combined size of hello world. People wouldn't even care. They'd go way over and say something like this and do this, basically. So
Yeah.
you'll see them do stuff like that, and free here is
Is
causing an
it
error
really
because
just to
that's
kind of like optimize
unallocated.
memory? Because like
So
you could
the
give like
reason I'm allocating is because 99% of the time you have no idea what these strings actually are. You don't know
yeah.
what the length of these are. Say these are coming in as parameters and this is some function, right? You
Mhm.
all you know is that this is C1 and C2. You don't know the length of these at all. And when you don't know the length of these at all, the only option for doing something like this is to make it big enough and pray that it works, and you should never do that, or you can dynamically allocate enough memory for both of them when you do your combination. So that's you have to dynamically allocate if you don't know how big C1 and C2 are going to be. There's no
Or
other
else you'd
option.
get or else you'd get. I don't want to say well. I mean, I guess you could say overflow, but not really. It just writes over other memory in the in the text.
Yeah,
Um,
exactly. So string copy here, it again, this would be it would be an overflow here because effectively what would happen is I'd string copy the contents of C1. I don't know what C1 is into C3. C3 only has 20 bytes of memory. Say C1 has a gazillion bytes of memory. You write right into that huge unallocated space of the stack right here. So
mm.
eventually you're going to crash into the heap and start overwriting things in the heap as that goes further down. But it's you should never do anything like this.
Oh yeah,
This
because we're in the stack. I forgot you said the const. Yeah, const strings are in the text, right? That's in the
Yes,
yeah.
const strings that you've declared as basically, so these are basically treated as these are in text. And there's other const strings that could be in other areas. So another const string that we actually didn't talk about is, let's look at C in memory. And yeah, memory layout of programs. One of the things we didn't talk about is command line arguments and environmental variables. So if I actually don't remember how to do this on Windows, is it like get env? That might be Linux. Env. Yeah, okay. So there's a bunch, when you run your program, you actually have access to all of these environmental variables that give you information about the computer that you're on. And all of these are stored as strings above the stack at the start of the program, like up here. So you can actually get pointers to these through C library functions. And this is all const char pointers effectively. And so it's not just your own custom strings, but it's also strings being passed to you by the operating system, by the compiler, and they're in all sorts of different stuff. So up here is the command line arguments. Any command line arguments you passed in are also stored as strings up here, effectively. So what this means is you have no idea if a const char pointer is going to be something that you can manage. So, for example, I have full access to my environmental variables. Look at this environment. So the path, which has all of your sys stuff on it, this is massive. Look at this. This is like 500 characters plus, right? So you don't want to take the risk of saying, oh, yes, it's fine now. I don't actually care. I'm just going to have this be like 20 things. No, you should always assume, you should always dynamically allocate in this case because you don't know what C1 and C2 are when writing the program,
So
especially if you're passing something in here.
if I append Harry Potter and the Goblet of Fire to my environmental path, miring path, that would be a bad thing if I only put 20.
Exactly. Yeah, you want to always dynamically allocate when you don't know the size of the string, and you want to use string length to actually get the length there. So again, you can't do something like this. This isn't valid C code. This will crash on us, and no, it won't. What? Excuse me? Excuse me? This isn't compile time legal in C. In C++, this would work, but this should not work in C. You're kidding. You're kidding. No, no, I absolutely refuse to believe that this is valid C code. Yes, you can compute this at compile time, but this isn't const expr. What? What C standard are they on right now? You know what? They've done some trickery in the latest versions where this is legal, but don't let them fool you. That's not legal. Don't don't do that.
Yeah.
Because they know that C1 is because we've defined C1 here during compile time, so they know the size at compile time and can just turn that in. But don't actually do that. If you
Does this
didn't know
use
what this was and it was a function parameter, you couldn't do that.
does this
Anyway,
use C99?
I actually don't know what C version on this is. If I type dash dash version into the compiler options, what do we get? GCC C. They're not gonna actually print out what version I am. Tragic.
No.
I might be able to get it if I go into the compiler and then switch over to. I'm gonna turn off library functions, directives. Now there's a ton of fancy information stored in here by the compiler that this is all like the random junk that you don't get to actually see. GCC compiler. This is all the stuff we were seeing in that C file . But effectively, C17. Okay, that's why it's happening. This is the latest version of C where they've added some trickery and const expr, which is very popular in C++ because it lets you do trickery like that. But we're not doing that. As far as we're concerned, we can only allocate set amount of bytes on here, without worrying about compile time stuff. Anyway, um, we're getting close to the end of the meeting, so why don't I just briefly cover some of these other functions? So we did stircat. Here's stirncat, and this is up to the number of characters that you specify. So this is what you were talking about, Matt, where effectively you're concatenating, but you're only concatenating up to count. So if the string is longer than that, you ignore effectively. So pretty straightforward. You're just putting in a condition that stops you right there. strxfrm. I actually have never used strxm. Transforms null terminated byte strings pointed by source into implementation defined form, comparing two strings with strcomp. Gives the same result as the original strings with strcall. I don't even know what strcall does. Okay. I'm gonna ignore this one for now. Let's take a look at an example. Okay, so this looks really more to me like it's something for cross compatibility. We really don't care about cross compatibility. We can ignore this one. strdupe allocates a copy of a string. Wait, returns a pointer to a null terminated. Oh, so this like dynamically mallocs a string. Returns a pointer to a null terminated string, which is a duplicate of the string pointed to by source. The pointer must be freed. Oh my god, this is exactly what we were looking for before. I know that this was its own separate function. I was dynamically allocating. But effectively, I guess the best way to copy a string then to something that you can actually talk to is star. So C3, give me a second here. So instead of dynamically allocating all of that, I'm just going to say, okay, so we're just going to do one right now. If I have char C3 equals strdup, and now I pass in C1, effectively, this should dynamically allocate end copy. So this basically functions as dynamically allocating and copying, but I do have to free the pointer returned to this. So I'm duplicating C1, copying it into something that's mutable, and so I can do stuff like C3 change. Let's do the thing where I change the first character to a J. And why are they mad? Semicolon. And look at that. Yeah, so strdupe basically all it does is it does the dynamic memory allocation for you. So it copies and it dynamically allocates and copies whatever was in here. So yeah, I guess they've added a bunch of useful tools to help you dynamically allocate. Okay. Then what we're looking for is okay. So sterndup allocates only up to a specific size, which contains copies of at most size bytes. Okay, yeah. Makes sense. Um, Let us now look. Let's see. So this stuff down here, this is some of the most used stuff. So strlen, very simple, returns the length of a string. It basically just goes through characters until it hits the null terminator. easy peasy. Str comp compares two strings. So this returns a bool if the strings are the same, and otherwise it returns. Let's see. So 0 if they're equal, negative values if LSH. I still don't fully understand this. I'm just going to pretend it's a bool. I've never used strcomp for anything other than checking if two strings are equal, right? Because you can't just check with the equality operator because you're checking pointers, right? So if you did C1 hello and then I had C2 hello, these would actually be okay. So there actually is a chance that this does work. There's a very small chance that this actually does work. So I'm going to printf something on the condition. Print out. It was supposed to be meme, but whatever. If C1 equals C2, then we're going to print out meme. And the reason that this prints out meme, do you know why this prints out meme? Take a guess as to why this prints out meme. The reason that this actually works and these two pointers are equal, the reason it's not because hello equals hello. It's because they've basically optimized the hell out of this to the point where they're saying, all right, we're not even going to bother to store a second copy of hello. I know you've said to store a second copy of hello, but we're not doing it. We only have one copy of hello in text. And C1 and C2 are both going to be pointers to the same thing, so the memory addresses are equivalent. So, but you should not rely on this at all. This should never be relied on as, oh yes, the strings are actually equal to each other. I could very easily screw this up and have it be something that they can't actually optimize. In fact, I might even be able to do it by declaring this volatile. Well, you know what? Even better yet, why don't I do my black magic and declare this as a char C2 50 equals to hello, which I said never to do, but we're doing it anyway. As you can see now, these strings are equal, but it's not actually saying that they're equal. So what we do instead is we check the strcmp of C1 and C2, and this should return that they are equal, and it's not for some reason, and I am once again blown away by the C programming languages. Eternal. Oh no, it's if they're if it does equal 0, then it prints out. So it returns 0. It's false in the event that they are equal. Okay, so this is kind of counterintuitive. It's actually the inverse of string comp. So string comp returns 0 if the two strings are equal, 0 being interpreted as false by the if statement. So most of the time, if you want to compare two strings, you see strcomp equals 0, and then this statement is true if the strings are equal to each other, because it uses the additional plus and minus information to talk about the other like if a string comes before another string, blah blah blah. I think it's alphabetical order. I'm not entirely sure. I don't really remember how strcomp works beyond just checking if two strings are equal. Okay, so strcomp, straightforward. What's another thing that we care about? Str is chr, returns a, let's see, what does it return? It returns a pointer to the first instance in which the character is found. So this is actually pretty straightforward. I'm not even going to type this up. I'm just going to explain how it works. If we have hello here and then we pass C1 into our where is it? strchr. So we pass our string in and then the character we want to find. It then returns a pointer in memory to whatever. How have I lost this? To wherever. Let's say we're trying to find L. It's going to return C1 plus 2, that memory location. So that's the pointer to that memory location. So pretty straightforward for find char. I am going to start Xing out of things because it is starting to annoy me that I can't find Compiler Explorer and I'm clicking around like 50 times. Okay, strchar finds the last occurrence of a character, so this is just in reverse. It would find this last L right here, goes through and looks at the end. So next up is strspn. Let's see. So what does this return? I've actually never used this one. Returns the length of the maximum initial segment of the null terminated byte string pointed to by des that consists of only the characters found in the null terminated string. So it's like string find, where like you're finding a substring. I'm not actually entirely sure what this does. Can you give me an example? Let's see. So here's string. Here's low alpha. And let's see, spans low alpha. After skipping the initial lowercase letters from S, the remainder is, this is interesting. So it's like finding, I guess it's like finding the difference between these strings. So it's like removing everything that was in string that matches a character in this string. I'm not entirely sure why that's useful, but I'm sure there are use cases for that. C string, that's another one. Let's go to actually the str. This is one of the more important ones. This is finds the first occurrence of the substring in the string, effectively. So, for example, hello, say you wanted to find low and get a pointer to that, it basically searches the string for the substring that you're looking for and returns a pointer to that in the string. I think it returns a null pointer. Yeah, returns a null pointer if the string is not found. So you can actually check pretty easily if the string is in there. And then finally, string talk splits a string into different arrays, and we will not go into this right now because the meeting is essentially over, and I don't want to go too overboard. The only other things I want to talk about is I wanted to talk about the mem functions, but we might save these for tomorrow since these are fun. Um, the homework that I want to give tonight, I haven't written down, but effectively, let me pull it up. I'm going to post it. I know this sounds terrifying. It's not as bad as I'm making this out to be. I would like you to implement as much of string.h as possible on your own. So I want the best way to really learn string.h isn't to use string.h, it's to write string.h from scratch. So I don't want you to write these. These are all in stdlib. I don't want you to have to do the conversions. What I really care about is that you write the easy ones. So strcopy, very easy function. It's like a for loop, right? strncopy, for loop, but it breaks on some condition with the n right there. strcat, again, it's like two for loops. Don't take my word for that. There's obviously a lot of other ways you can do this. There's while loops, everything. You could do all of these recursively as well. Str and cat, again, same thing as cat, but there's breaking in there. Str dupe, this is literally just a malloc and a copy. Str and dupe, it's literally this, but with the breaking condition version of one of those. Str len, you literally just loop through until you find the empty character. Str cmp, you can compare character by character until if they're equal or not, and until you hit the end of both strings. Strns comp, same thing. Str col, we're not. I don't even want this, but effectively write as much of string.h as you possibly can. Just do the functions that you think would be cool or interesting. Preferably, if you're going to go for a minimal implementation, at least try and get strcopy, strcat, str len, strcmp, and str. I'd say those five are the most important ones. I'll write those down right now in the thing. Let's see. So homework. Yeah. Okay. We didn't even go over stdio.h. I should have read this before. I was supposed to go over files today. Oh my god, I don't know what I was doing. I was just like, oh yeah, it's string day today. We're doing strings, and it went over strings exclusively. I am sorry. Okay, so your homework is going to be write as much of string.h as you want. Preferably, and I'll have these in order of easiest to hardest. strlen is the easiest function. The other things that we have in here are, let's see, strcmp is also pretty easy. Shouldn't be too bad. Oh, okay, that literally just copies strcmp. Okay. Preferably the n I don't really need the n versions. I'm not like, oh yes, write the n versions for me. I don't care that much. Let's see. Did I have strcpy already? I'm going to yeet this. Goodbye. That didn't put things in the right version. Oh my god. I hate this formatting. This is terrible. Okay, I'm gonna actually just get rid of these. strcmp, strcpy, strdup, and let's see. Anything else I can have you guys do that's like I really think that you should? I want those fancy schmancy things. Let's see, what else do we have down here? String copy, stir cat. Did I do cat? I do have cat, right? Land. I don't know if I have cat actually. You should totally write cat. Cat would be probably one of the hardest ones. strcat. And when I say hard, I mean like it's gonna be like maybe 10 lines of code. These aren't that. these really these really aren't that bad. str span would probably be pretty hard, but I'm gonna put that in there as like the challenge one. Why not? Um, and the only other one I could possibly want is str, which finds a substring. str. Okay. And I'm gonna just rewrite that str-spn. Okay, so I would like, as much as you're comfortable writing string.h, write as many string.h functions by yourself without using other string.h functions. So you can use the functions that you wrote yourself. So but I don't want you to have your stringlang function call stringlang, obviously. I don't really want your string comp function to call their stringlang. You can if you want, but I'd rather have it call your stringlang that you've written by yourself, right? So this is going to be, obviously you can call malloc for stuff like string dupe, because that's literally what string dupe does. It mallocs and then copies, right? So you can call your string copy from strdupe and malloc, right? So call those library functions. But other than that, I think that this is good. And make sure when you're writing this to use best C practice. So have a header file, have an include guard, and have forward declarations for all of your strings, and compile them to object files, and then make a driver file. So this will be I think that this is a fun challenge. Obviously, not everyone has a ton of time to do this, so don't worry. I will, if you want, you can send me submissions for this. Um, all winter if you want. You don't have to submit it tomorrow if this sounds fun, but you don't have time for it. It's fine. Anyway, I think we're going to wrap things up for tonight because we're like 12 minutes over. Tomorrow we're going to be going over enums and unions, which are like the weirdest C structures, and I probably need to brush up on them before I start talking about them because you can do some wacky stuff with unions. Enums aren't anywhere near as bad. Anyway, all right, so I'm going to wrap things up for tonight. Have a nice night, guys.